This is Lecture 2 from Module 1 in the book Problem-Solving Guide for Electromagnetism and Optics, 3rd edition. In this lecture, we will be introducing the concept of an electric field and solving a problem involving electric fields produced by point charges. Lecture 1, we talked about electrical force. One charge exerts an electrical force on another charge. This type of calculation can also be done using the concept of a field. And you should be familiar with this concept from the first semester of physics. When calculating the gravitational force on an object, we use the concept of the Earth's gravitational field. The Earth's gravitational field is 9.8 newtons every kilogram, and it's downward. 9.8 meters per second squared is the same as 9.8 newtons per kilogram. The units are the same. The electric field is similar. The units of electric field are newtons every coulomb. You get the force per charge. Gravitational charge is mass. The gravitational field gives the force per gravitational charge, force per mass, newtons per kilogram. Electric field, newtons per coulomb. The equation that gives the electric field a distance r away from a point charge q is E is kq over r squared. That's the magnitude of the field, a distance r away from a point charge q. Once we have the field, we can calculate the force with F equals QE. So the force on a charged particle immersed in an electric field is QE. Q is the magnitude of the charge, E is the magnitude of the field. This equation is exactly analogous to the force on an object in a gravitational field. What equation do you think that is? F gravity is mg. G is the gravitational field, m is the gravitational charge, which we call the mass. There's a difference here, and we have to think about the direction of the electric field. There is a difference between electrical forces and gravitational forces. With electrical forces, we determine the direction of the force based on whether the charges are like or unlike. If they're unlike, it's an attractive force. If they're like, it's a repulsive force. We don't have that in gravity. With the electric field, there's one equation, kq over r squared. There's one q in there. Is the field attractive or repulsive? We know the gravitational field's always attractive, but the electric field can be repulsive. The gravitational field can't be repulsive. We know the direction of the gravitational field lines. They're towards the mass. The gravitational field of the Earth is towards the center of the Earth. There's G. It's simple. Electric field is more complicated. We need a convention. We could define it towards a positive charge, or we could define it away from a positive charge. It doesn't matter how we do it, but we have to make sure everybody understands and uses the same convention. So if this is a positive charge, which way is the field? Is it towards it or is it away from it? Could be that, could be that. Well, we have to make a decision, and we made a decision, and it's this. The convention for the direction of the electric field lies is in the direction a positive charge would accelerate. So if this is a positive charge, the field it produces is away from it. If we put a positive charge there and let it go, it's going to accelerate away. And it's just a convention. Electric field lines are in the direction a positive charge would accelerate. So let's look at some charge distributions. This is a great way to try to wrap your head around fields. Imagine the relative strengths and the direction of the field lines produced by a series of charges. We'll start with two equal positive charges. 1, 2, equal magnitude, same sign, they're both positive, and we'll pick some points in space and think about the field that's produced there. So here's one, above the second charge. Where's the field here? This guy is producing a field straight up. directly away from it. It's a positive charge. If I put a positive charge here, this one would push it away. This one would also push it away over in this direction. But it's weaker because it's farther away. E is kq over r squared, so there's a weak vector here, a strong vector here. It's going to be something up in that direction, like that. Let's pick another point. How about over here? This guy's pushing away. This guy's pushing away. The field's going to be directly away from both positive charges, like that. They're both pushing in the same direction. How about directly between them? This guy's pushing that way, this guy's pushing that way. The charges are equal magnitude. The fields are in opposite directions. The field is 0. How about here? This guy's pushing this way. This guy's making a field that way. The field should be straight down. If I put a positive charge here and let it go, it should go straight down. And indeed it does. Pick some points yourself. Put 3 charges on there. Put 4 charges on there. Try to figure out the direction of the field. It's good practice. Good way to wrap your head around electric fields produced by charges. Let's do another one. This time, we'll make the charges opposite sign. Equal magnitude, opposite sign. Here's a positive charge. Here's a negative charge. And let's pick the same points. Up here, this is a negative charge. It produces a field directly toward it, and it's strong relative to this one. This guy's still pushing up that way, making a field in that direction. It's going to be like that. Down and this way. This guy's pulling it down strongly. This guy's pushing it away, so it's going to be like that. Over here, the negative charge is producing a field toward it. Positive charge is producing a field away from it, but the negative charge is winning because it's closer. So if I release a positive charge here, it's going to go that way. How about between them? The negative charge is pulling a positive charge toward it. Positive charge is pushing a test positive charge away from it. It's going to be big field to the right. Down here, positive charge is pushing it away this way. Negative charge is pulling it this way. I have a vector here and a vector here. They're the same distance away. The charges are the same magnitude. The vectors are the same length. One vector from the negative charge is that way. One vector is that way. If I add them up, I'm going to go that way, to the right. It's smaller than this one. All right, now let's do a problem. A plus 2 nanocoulomb charge is 5 centimeters from a plus 6 nanocoulombs charge. Where is the electric field 0? Tell me where there is no field. As always, we start with a good diagram. There's the plus 2, there's the plus 6, and let's think about where the field's going to be 0. Both charges are positive, right? So the field over here is to the right. If I put a positive charge here, it's going that way. If the field over here is to the left, if I put a positive charge over here, it's going to accelerate to the left. If I put a positive charge up here somewhere, both are pushing. It's going to accelerate up. If I put a positive charge down here, it's going to accelerate down. The only region where it's possible that the electric field 0 is directly between them. If I go close to the 2, the 2 needs some help because it's so weak. So you got to go closer to it. Somewhere in here, the 2 is pushing that way. The 6 is pushing to the left. 2 is pushing to the right. And there's going to be a place where they balance. If I go close to the 2 is going to win for sure because the distance is so much smaller. Once I get over here, the 6 is going to win because it's bigger. It's going to be somewhere in here. So let's define a distance. Let's call a distance from the 2 x, and then calculate the field at that point. So there it is. If the fields are the same at x, We know they're in opposite directions. If they have the same magnitude, the field here is 0. Now let's calculate the field at distance x from the 2 nanocoulomb charge. The field is the vector sum of these two fields, and we know they're in opposite directions. So let's get the fields individually. The magnitude of the field at distance x from the 2 nanocoulomb charge is kq over r squared. The field produced at distance r away from a point charge q is kq over r squared, and we can plug in the numbers. There's the k, there's the 2 nanocoulombs, and it's x away. We don't know what x is yet. That's what we're solving for. Now, how far away is the 6 nanocoulomb charge from the point at which we're calculating the field? Well, the total distance is 5 centimeters. So the distance is 6 away. The distance the 6 nanocoulomb charges away is 5 minus x. 5 centimeters minus x. So we have k, q, that's the 6 nanocoulomb charge. The distance away is 5 minus x. There's no charge at this point, right? This is empty space. If we were to put a charge there, doesn't matter the sign, it's not going to move because the electric field is 0. So now we can calculate x. We set the magnitude of the field equal to each other. The electric field produced by the 2 nanocoulomb charge is this. The electric field produced by the 6 nanocoulomb charge is this at the point x away from the 2 nanocoulomb charge. And we can start doing some math. We cancel the k's, get rid of the nanocoulombs, and we get this. We can cross multiply. And instead of foiling this out, we can take the square root of both sides. The square root of 2, and then we only have 5 minus x. And the square root of 6x squared is the square root of 6x. And now we can distribute the square root of 2 in there. We can put the square root of 2x on the other side. And we can factor out the x, divide by square root of 6 plus the square root of 2, and get the distance, 1.8 centimeters. So the electric field is 0, 1.8 centimeters away from the 2 nanocoulomb charge in the direction directly toward the 6 nanocoulomb charge. And that's the answer to the problem. So here's some takeaways from Module 1. There are two types of electric charge. We call them positive and negative. Unlike charges attract, like charges repel. The magnitude of the force between two charges, Q1 and Q2, that are at distance r apart is kQ1, Q2 over r squared. K is Coulomb's electrical constant, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Problems involving forces on point charges produced by other point charges often involve summing multiple forces to get the net force. Forces are vectors. The conventional way to add vectors, you break them down into horizontal and vertical components, and you use sine and cosine to do that. Then you can sum all the horizontal components, sum all the vertical components to get the net horizontal and net vertical component. And then you have two vectors, the force in the x direction, force in the y direction, and you can use the Pythagorean theorem to get the magnitude of the net force and arctangent or other trigonometric function to get the direction of the net force. The electric field produced by a point charge q a distance r away is kq over r squared. The direction of the field conventionally is the direction a positive test charge would accelerate if you put it in the field. The magnitude of the force on a charge immersed in a field is QE. F is QE, Q is the electrical charge, E is the force per unit charge, newtons every coulomb. That's how you get the force. If the charge is positive, the force is in the direction of the field. If the charge is negative, the force is in the direction opposite the field. There's two types of charge, and we have to account for that. Problems involving electric fields often involve summing the fields, getting the vector sum of the field from different charges. At a given point in space, fields are vectors. You have to add them like vectors. So you may be watching this video thinking, I understand this. I got it. I can follow along. But just as watching someone else juggle does not make you a good juggler, watching someone else solve problems does not make you a good problem solver. Watching someone else swim does not make you a good swimmer. Watching someone else play the piano does not make you a good piano player. You have to practice. You have to solve a lot of problems. There are a lot of good, challenging problems at the end of Module 1, Supplementary Problems, in the book Problem-Solving Guide for Electromagnetism and Optics. So let me talk about becoming a good problem solver. So start with a good diagram. Invest, don't spend, invest time understanding the problem thoroughly before plugging numbers into equations. What's going on here? How am I going to get to the solution? Wrap your head around it. If you can't do it, resist getting help for as long as reasonably possible. Try to figure it out for yourself. Don't think, I don't know what I'm supposed to do. There's only one thing you're supposed to do when solving problems. Think hard. Try to understand it. This is the benefit. This is the time in which your mind develops. Thinking hard, trying to reach a new level of understanding, trying to solve a hard problem. The more time you invest trying to understand the challenging concept, the more your mind develops. This is the goal right here, developing your mind. As soon as you say, I need help, somebody tell me how to do it, you're giving up on developing the ability to independently reach a new level of understanding. There's nothing wrong with getting help after you struggle for a while. But as soon as you get help, oh yeah, I see that now, you should immediately start another problem. So you can restart the development of your ability to figure things out for yourself. So the longer you try to solve a hard problem, when somebody tells you, when an expert gives you advice, oh yeah, now you'll appreciate it much more. You'll be able to apply it more in the future, and you'll fundamentally understand the concept. You'll develop your problem-solving intuition as a result. You'll be able to solve problems quicker and more efficiently. When you're stuck on a problem, the longer you try to figure it out for yourself, the more you will develop the ability to figure things out for yourself. This is not surprising. If you practice anything, you're going to get better at it. So my hope is when you get a hard problem that you have no idea how to do, you've never saw it before, instead of thinking, oh my God, I don't know how to do this problem, I better raise my hand and get some help, like a sheep would, you're going to say, oh, I have no idea how to solve this problem. I've never saw a problem like this before. What an opportunity to learn. What an opportunity to develop my personal problem-solving skills. I cannot wait to get started.